Before we look at the metric for curved space-time, we're going to look at the Minkowski metric again, and we're going to express the Minkowski metric in polar coordinates, and we're only going to do this in 2 dimensions. So if we were writing the Minkowski metric in 2 dimensions, let's say we have c dt squared minus dx squared minus dy squared. Rather than using x and y, though, in polar coordinates, if we move in the radial direction, this would be dr, and if we move in the tangential direction, this wouldn't be just d phi. You'd have to use the arc length formula to get this distance, and that would be r times d phi. So in polar coordinates, our Minkowski metric becomes c dt squared minus dr squared minus r squared d phi squared. Okay, now for our metric for curved space-time, there's going to be a factor in front of the dr squared and a factor in front of the r squared d phi squared. Now, what happens if you multiply the dr squared by something? Now, let me find where this is. If the radial part of the metric was multiplied by a factor that got large as r got small, this would result in a coordinate system that looks something like the one that we have at the left. So if let's say there's a large massive object at the origin. So if you're over here, if you take a step in the radial direction, it has this length. But as you get closer to the origin, when you take a step in the radial direction, that step is larger. And they say, notice that there is really no way to adequately draw this coordinate system on a flat surface. The coordinate system is intrinsically curved. So this is actually what our curved spacetime is going to look like if there is a large massive object, such as the Earth, at the origin here. But it doesn't actually mean that spacetime is going down in the vertical direction. It's rather due to our limitations of trying to represent this on a piece of flat paper. So now we are ready to take a look at the Schwarzschild metric, which we use for general relativity. So the Minkowski metric was for flat space, whereas the Schwarzschild metric is for curved space. And space-time is curved because of mass and energy. Now, we are going to be limited in how we use the Schwarzschild metric. So you see we have a mass here. That could be the mass of the Earth, or it could be the mass of the Sun. But that mass has to be at the origin of our coordinate system. So we are not going to be able to look at how space-time would be affected by 2 large massive objects, because we always need to have the mass at the origin of our coordinate system. You could look at how a mass such as the Sun would affect another mass, such as a spaceship or people on a spaceship over here, but you cannot look at how 2 different large massive objects would be affecting something over here. Okay, so we have our Schwarzschild metric here, and we have some important points for our Schwarzschild metric. So the metric is for a slice of space-time that contains the mass center. Since the mass is spherical, all slices through the mass center are identical, and the metric is expressed in polar coordinates with the mass center at the origin, which is what we just said. And because the masses are spherical, it doesn't really matter that we are restricting ourselves to looking in 2 dimensions. The tangential component of the metric is the same as what we had for the Minkowski metric. So back here, we looked at how if you go in the radial direction, the steps are becoming larger, but nothing's changing in the tangential direction. So this is what we would have had for the Minkowski metric, and that's the same as what we have here. Both the temporal component and the radial component are deformed by multiplicative constants, which is what we have in parentheses here and in the denominator here. So the radial length and the time interval would both be different depending on where you are in space. Now, it shouldn't surprise you that if the large mass that we're talking about is 0, we should get back the Minkowski metric, because if you don't have any mass deforming spacetime, then you could use the Minkowski metric for flat spacetime. So if this mass is equal to 0, this term is 0, so that would just be 1 times c dt squared, which is what we would have for the Minkowski metric, and same thing, the denominator here would be 1, so that would be the same as what we would have for the Minkowski metric. T, which is, well, related to the dt that we have here, is the flat space-time. This is measured on clocks very far from the central mass where space-time is assumed to be flat. So if you have your large massive object here, the farther away you go from that large massive object, the flatter space-time gets. So dt is measured on clocks that are very far away from the mass, and then you can treat that as being flat space-time. The r that we have here and here and here, that is the reduced circumference. And the reason, I mean, it's called the reduced circumference, but it's actually more like a radius. If you try and measure the real radius, see how this just keeps going down and down? So the closer you get to the origin, the larger each step in the radial direction becomes. So you wouldn't be able to measure the radius that way, but what you can do instead is, say you are here and you want to know the distance to the origin. Instead, you could say, if I went and measured this circumference and then took the circumference and divided by 2 pi, that gives me the reduced circumference. But it's actually, like, it would make more sense if it was called the reduced radius, because the r is actually like a radius and not a circumference. And finally, there is a special place at which the metric becomes infinite. So if you look at the denominator here, so we have an r, which depends on where we are relative to the origin. So that would have been like our location here before. If 1 minus 2gm over c squared r is equal to 0, then this fraction blows up, and that would happen when r is equal to, let's just use what they have here. So when r is equal to 2gm over c squared, and if we put that in here, this whole term would become 1, and we would have 1 minus 1, which is equal to 0. So a single radial step at this location is infinitely long, and it appears that a single clock tick has no duration. This radius, or reduced circumference, is termed the Schwarzschild radius and forms the event horizon of a black hole. At or within this radius, events are beyond the horizon, meaning they are unseen and unseeable from radii greater than the Schwarzschild radius. Basically, once you pass the event horizon, you are no longer in contact with the rest of the universe. So this is the event horizon radius. And so if you have someone in flat space over here and they're observing something that's happening close to the event horizon, once an object passes the event horizon, the person back in flat space over here can no longer observe that object. And we'll talk more later about what actually goes on then.